Welcome to the demonstration corner. Today we're going to talk about the temperature platforms that are available on the MP-1. But before we do that, we're going to just turn the camera around and show the methods that are available for demonstration and one-on-one training and after-sales support. So turning the camera to this side, we have the guarded heat flow meter, ASTM E1530, for measuring complex materials. The guarded nature of it, being a steady state, allows you to layer non-repeating layers and get a high confidence one-dimensional heat travel for thermal resistance. It auto measures thickness, so you get a result of thermal resistance and thermal conductivity. So ideally suited for complex structures that are non-repeating through the thickness and or heterogeneous. Temperature range, full temperature range, -20 up to 310 Celsius, plate temperature. So again, ASTM E1530. ASTM C518, this is our heat flow meter for measuring construction and insulation materials. This is our HFM100, which is our larger model, which is sample sizes up to 300 by 300 by 100 millimeters thick. The plate temperature available on this model is -20 to 75 Celsius. There is a high temperature version, which is -30 to 110 Celsius. And then we have a small HFM50 for measuring sample sizes of 200 millimeters square by up to 50 millimeters thick. And turning the camera the other way, this is the MPV. This is our new addition to the MP family, measurement platform family. MPV standing for versatility. This combines transient plane source for solids, pastes, and powders according to ISO 22007-2. That would be the transient plane source method, as well as the transient hot wire method. Following ASTM 7896 for thermal conductivity, thermal diffusivity, and specific heat on solids and phase change materials. So we brought this together as a mid-range offering of the measurement platform due to customers' interest in a mid-range instrument. So we'll be doing some demonstrations on that next week. This is the THW-1. We did a demonstration on this yesterday. This is a standalone transient hot wire following the same standard that's available on the MPV. It's ASTM 7896 for thermal conductivity, thermal diffusivity, and volumetric or specific heat or mass-based specific heat for liquids and phase change materials. This has an integrated temperature platform, which has a whole range if you need it, from cryogenic up to 300 Celsius and back pressure up to 35 bar, which is for testing past boiling points. There's a few ranges of temperature mixed in there. Going down the other end of the bench is our baby heat flow meter for measuring small format construction materials and insulation, and then our entry-level MP2, which is the baby brother to the measurement platform series, and that has transient plane source sensor, transient hot wire sensors, and transient line source sensors, which is a high accuracy, intelligent little meter for measuring basic applications. So coming back to the MP-1, we wanted to spend a little bit of time showing the measurement platforms. Again, those work in concert with the MP-1, the temperature platforms do, because of the expandability. So every MP-1 controller can be purchased with a temperature platform for the transient plane source method or the transient hot wire method, or any combination thereof. There's 4 channels on every MP-1 controller, so you can make a measurement at room temperature on the bench with both methods. This is just the sample holder for transient plane source. We have a transient hot wire equivalent, room temperature bench measurement. And you can connect, if you need it, the ability to measure temperatures with the temperature platforms. We have some customers that look for 2 transient plane source temperature platforms side by side, so any variation of. There is a MP-1 switch demo where we show all the variations to sort of generate the ideas. If you have a high volume or diverse range needs for your lab, how you can package the MP-1 together with the various channels, working with the platforms to sort of maximize your requirements. So with the smart software, which allows us to schedule everything and take advantage of the transients being short test times and each device needing to control temperature, the 4-channel switch and smart software let us orchestrate all that in a convenient, rapid manner. So what we really want to show beyond that switch and discussion of that is the temperature platform. So we're going to bring the camera in and talk a little bit about the transient plane source. We have this disassembled just to sort of show full out what the steps of assembly would be, and then you'll be able to see it fully assembled. And this is our transient hot wire temperature platform, which we'll show next. So the basic TPS temperature platform is 0 degrees to 300. And of course it's all self-contained, both the control of it as well as several safety features. The 0 to 300 does not require any external cooling. It's all done by a proprietary cooling and heating design. And if you want to go colder than 0 degrees, we have different cooling options. So there is a minus 45 degrees Celsius cooling option and a minus 160 cooling option. And those work in concert with the design of the temperature platform to offer that full range without having to remove the sensor and move it to different temperature devices. And on the THW, the basic temperature range of what you see here is 10 degrees to 200 Celsius, but it can be expanded with similar types of cooling and heating methods to go all the way from minus 160 Celsius up to 300 Celsius. So the basic one is 10 degrees to 200 for the transient hot wire, and the basic transient plane source temperature platform is 0 to 300. So let's set up a sensor first. So of course from our different demonstrations you've seen our sensor. This one is 3.2 millimeters radius or 6.4 millimeters diameter. 4 contact points. Those are made outside the heating and cooling. So that's unique in a couple ways. One is it maintains longer life for the sensors because less of the sensor is exposed to the heat, but the 4 contact points are made outside the heating with these there. So I have this disassembled. We don't normally have to take this off, but I thought it'd be kind of neat to show what the contacts look like. So we put these facing down, and there's a cutaway to show where the sensor goes. The plate that we use to secure the sensor to the contact points has a mica board which electrically isolates, and if you were to ever overpressure the contact, those individual electrical contacts won't poke up through and short out your sensor. These are knurled knobs which basically stay there permanently. I just again disassembled it to show what that might look like. And then when you want to secure your sensor, you just spin these down until they stop just off of mild turning, and then just a quarter turn each, and then you know your sensor's secure. There's a step in the software that we say test the electrical resistance, and that confirms that the sensor is electrically connected before any measurements are made. So the floor of the temperature platform goes up and down. So I'll sort of gently move the sensor out of the way so you can sort of see what that looks like. And that accounts for different height of your sample. So we're going to actually test Pyrus RAM. The pieces of Pyrus RAM are roughly half an inch or 12.7 millimeters diameter. And so I raise the height of that floor so that that sensor is sitting relaxed horizontal. So we center the sensor. So the maximum dimensions of the transient plane source temperature platform is 40 millimeters diameter, up to 40 millimeters diameter, and up to 20 millimeters thick. This is a couple pieces of stainless steel that show those exact dimensions. It shows you the largest that you could test inside of here. We do offer off-the-shelf ovens available for the temperature platform that allow you to measure up to 100 millimeters square and up to 2 inches thick. So this is our convenient research scale temperature platform. So that gives you an idea of the maximum. That's per side. So when we're ready to load our second piece, if you're doing symmetric testing, if you're doing asymmetric testing, of course, you would one of those sides would be insulation. That is just an introduced metal plate to make sure we're not scarring our sample. So that's your setup for the temperature platform. We're going to do it in assembly. So this is our heating. We're closing out the heating side of the sample setup. So I'm just backing this off. We secure the heating. So there, and then we turn this one just to give us good contact between the sensor and the sample. That just needs to be thumb tight. We do offer for materials that are compressible, we do offer this same set screw with spring-loaded plunger in it, which allows you to vary the pressure or maintain a pressure. So this one's just a solid set screw. We do have these with individual plungers with a spring inside to allow you to vary the pressure. This closes out the cooling. So the way the temperature platform works for the temperature platform for the TPS is you have cooling on the outside. So this closes the cooling part of the temperature platform. And this portion around the sample is the heating. So you have these opposing temperatures that works really good in partnership to give you precise control of temperature and fast to temperature stability. And this is the last step. This is our lid. This has a magnet in here which closes an electrical connection underneath here, which tells the system. You can see here the lid says off. As we put the lid on, that will go to lid on. And now we're ready to go to the software and set up an experiment. Before we do that, we'll set up the transient hot wire and talk about that a little bit in much the same way. And then we'll go to the software and set up both experiments at the same time. So our transient hot wire sensor, this one's empty. We're going to put ethylene glycol in it. This holds about 20 milliliters. This is our transient hot wire sensor, stainless steel construction, platinum wire clamped between two contact points. You can look at other demonstrations for more details on that or contact us. But this is an ASTM for measuring high accuracy thermal conductivity, thermal diffusivity, and specific heat of liquids and phase change materials. So when it comes to phase change materials, we have different cells that account for different changes in volume. There's a spring-loaded cell that allows you to measure materials that change in volume, yet maintain the contact with that change in volume with the wire, which is key to making good measurements. So that's our phase change material cell, our PCM cell. So we're going to load, want to do this in front of the camera so you can sort of see the steps. We're going to load our ethylene glycol, which is, in this case, about 20 milliliters. So I basically load it until it is near the top of the cell. And we're going to put our sensor in here. I'm just going to lift this out, turn it. There's a O-ring that if you do want to apply back pressure, if you're going to test past boiling points, you can apply back pressure there. The two different back pressure ranges are 20 bar and 35 bar depending on the sensor you have. So once you have your sensor loaded into your liquid, you place it in the temperature platform that's designed for the THW. And it works much the same way, it's just concealed. But you have a cold and heating opposing temperature to provide high accuracy control of temperature for the transient hot wire, just like the transient plane source. So in this case, we're setting up two experiments for control of temperature with the two available temperature platforms on the MP-1. So we'll share the screen. So right now we have I've already started, first step, I already renamed the sample. I named where to save the location of the sample, and we're going to run PyroSram, symmetric, isotropic, and semi-infinite body. We've selected the temperature platform. Of course, we could select the room temperature measurement or the THW, which is what I will do for the transient hot wire step. The name of the sample is PyroSram. Those are the dimensions. I'm going to test the electrical resistance of the sensor. Normally right now I would run the ITPS, which is our automation for development of parameters, but to kind of keep this focused on the temperature platforms, we've already pre-run that, which identified 5 seconds and 80 milliwatts based off of the dimensions of the sample here. So generally for the ITPS, which is our intelligent transient element of the design of the software that automates all parameter selection, all you have to really put in is your sample name and your dimensions. So we go to the next screen, excuse me, and we're going to run an experiment from, let's say, a starting point of 0 to 300 Celsius. That's the full range of the method, the full range of the temperature platform we have on demonstration. We're going to use the power that the ITPS got. We'll do 5 measurements with a 10-minute delay. We'll add that to the schedule. You see it auto builds the schedule, 0, 50, 100, etc. Of course, you can populate that with a lot more increments of temperature. We can affect the stabilization here. These are all auto, which we encourage you to just leave. But that's a two-step stabilization. So it looks for stabilization of the chamber, and then it looks for stabilization of the temperature at the sensor level. So that where the sensor is sandwiched between two pieces of your sample, by looking at the electrical resistance over a short period of time, in this case 20 minutes, we can confirm there's isothermal conditions inside the chamber at the sample level. So by clicking start on this particular channel, which is port number 2, I believe, a schedule is set up for running PyroSRAM inside the temperature platform. You'll see the temperature change set to 0 degrees. If I change the camera and go back, you would see that. You can see that the temperature platform is now going to go to 0 degrees and then proceed through the steps. So while that's doing that, we can set up the software for running the THW. So I'm going to share the desktop again. Go back to, let's make a measurement. User, and we're going to run transient hot wire for liquids. I want to tell the system where to save the data. Ethylene glycol is what we're measuring. And then we're going to use the transient hot wire temperature platform. We'll just do ethylene glycol. We could note here the boiling point and pressure. That's just for your information. And this is the transient hot wire sensor associated with that port, which is port 3. We can check the electrical resistance. Again, it's just like the TPS sensor. It wants to make sure that you don't have a damaged sensor before you set up a schedule with temperature. And like the transient plane source, the ITPS, or the intelligent element of the parameter optimization or parameter selection, is automatic. So we could run a quick transient here, but we're just going to run a full schedule with temperature. So here we can say, let's go from the maximum temperature range of this device is 10 degrees to 200. Typically with transient hot wire, we run more points. Again, power is optimized, so we don't have to manually select that. We'll run 3 measurements with 5 minutes between each. Add that to the schedule. And here, now we've developed steps 10 through 200 degrees. Now, probably to get to 100 to 200 degrees, we would have to back pressure that sensor. I think the boiling point of ethylene glycol is around 180 or 185, but for demonstration. And then we can click start. And here we have 2 steps of temperature on 2 different temperature platforms that are set to schedule and run automatically. So that gives you an idea of the diversity and versatility of the temperature platforms working with this schedule. And this is your yet to be captured data screen as it proceeds through the steps of isothermal steps of temperature. That data will show up here. So this is your data acquisition software. So when you have data to review, it'll populate here, but the analysis application is what we offer for full analysis of data by whatever method you are using on your measurement platform. So here's PyroSRAM previously done, 5-second measurement. You can see the thermal conductivity with temperature. That gives you an idea on that. And here's our results, sort of tabulate it. Thermal conductivity, that's at 50 degrees. Thermal diffusivity and volumetric specific heat, and the statistics associated with that data. And we did a short range of ethylene glycol as well. So you can open up data from different methods and review it and look at the same tabular form like this. This is ethylene glycol at 10 degrees and 20 degrees. So the average is 0.25, and your diffusivity and your volumetric specific heat. And that lets you look at the same data, both the residuals and the bulk, as well as the thermal conductivity temperature. So, of course, that's zoomed in quite a bit. The repeatability is 3rd decimal place. So that gives you an idea of the temperature platform and the setup of each type of temperature platform and the steps of setting up a schedule and how the software and the switch and the temperature platforms work together. I invite you to look up one of our demonstration. We'll put it in the description below. Our demonstration that corresponds to the 4-channel switch and the mixture of temperature platforms that one can do, depending on your need and your volume, and whether you're testing solids or liquids. There's a lot of versatility that you can do within the MP-1. That concludes. If there's any questions, please get a hold of us. We're happy to answer them or set up a one-on-one demonstration. Otherwise, thanks for joining.